Welcome to our channel. This is our first video and I'm so excited right now because we're going to talk about a very popular topic nowadays. Yes, you're right, deep learning with a very popular framework. Yes, you're right again, PyTorch. This video will introduce the basic idea of deep learning through the PyTorch workflow. And before we look at the code, let's figure out one thing first. What's the deep learning? Um, if you just Google it, you will get an answer consisting of a variety of technical terms, which is not easy to understand. While in my understanding, deep learning is actually a process of finding a mapping function f between the input x and the output y. And with this mapping function, we can just provide the x and we get the results y. For example, x could be a set of images and y could be a set of labels, dog or cat. And if we input these images into our mapping function, then we get a label. Oh, it's a dog. And if we input this image into our mapping function, then the prediction could be a cat. The mapping function f is what we call the model in deep learning. A main difference between the traditional programming and deep learning is that in the traditional programming, we often need to manually design rules or features to distinguish cats and dogs, which is really difficult. Whereas in the deep learning, we just need to construct the model and the model will learn the parameters, also called the weights, from the training dataset. That's why the deep learning is so powerful. The first step is preparing our dataset. We generate our dataset using the Scalar package, which is pretty popular and commonly used. But for now, I think you can just ignore this code because this is not the main idea of deep learning. Anyway, let's just look at our dataset. We have two different colors of dots, red and green, and as you can see, they have something, decision boundaries between them can separate them into different classes. So we just need to find a decision boundary to separate them. And if there's a new dot falls in here, and we will predict the new dot as a red. And if there's a new dot falls here, and we will predict it as a green dot. But how can we do that? Alright, that's the magic of deep learning. And there's one thing you should pay attention, which is that we need to split our total dataset into two different subdatasets, which is the training dataset and the testing dataset. The model will train on the training dataset to learn the patterns. And after training, we will test our model on the testing dataset. Because, we already use this data during training. If we still test our model on the same dataset, it's just kind of like cheating. So we need the totally new unseen data to test our model to make sure that the model really learns something useful. Let's move to the most exciting part, constructing our model. Basically, a deep learning model consists of multiple layers. There are input layer, output layer, and of course, hidden layers. And PyTorch provides many pre-built layers, and we can check it through this link. Well, look at that. There are convolution layers, pooling layers, padding layers, normalization layers. There are so many different kinds of layers. And we just need to pick different layers and combine them together to build our own model. You definitely want to ask me, how can I pick these so many different kind of layers? How should I combine them? This is the most important idea I want to share with you. The answer is, sorry, we do not always know. Yes, we often don't know in advance which architecture is the best. Deep learning is a very experimental and empirical subject. If you have ideas about picking and combining layers in different ways, just try them and then check whether the results are good. Almost every day there are lots of papers proposing new deep learning model architectures to show different ways of combining these layers. So we usually construct our model based on experience and experiments. Yes, experiments and experience matters a lot in deep learning. Let's build our first model. A model is actually a Python class, and it inherits from the PyTorch n.model. There are two key functions inside a model. The first one is the init function, and second one is the forward function. The init function defines the layers inside the model and the activation functions. Here we just pick the n.linear as our, as the layer of our model. And if you want to know the exact mathematical process, we can check the documentation and find it here, linear layers, n.linear, and check the description. Applies linear transformation to the incoming data. Alright, this is the inputs x and this is inputs y. We multiply the inputs by a sort of ways is learnable, and plus a bias is also learnable, and then we get the results y. That's what linear layer does. But do you remember our task? If our model only use linear layer, which means our whole model is totally linear, and it can only learn the linear features. So can we set a clear decision boundary just to use a straight line? No, obviously not, because we want to set a clear decision boundary, so we just have to use a nonlinear function. That's why we need a ReLU. ReLU is a nonlinear activation function, can allow us model to learn the nonlinear features. And let's check the documentation. ReLU. Oh, look at that. It's not a straight line. It's nonlinear. Yeah, that's good. So that allows our model to learn more complex features than the totally linear model. And the forward function defines how the data goes through the layers. We input our data and through the input layer, and then we apply the ReLU function, and then we pass it into the output layer, and then we get the results. That's the forward propagation of our model. And we can instantiate our model after defining it. Let's run it. And let's run it. Oh, look at that. We have input layer, output layer, and our activation function ReLU. Oh, that looks good. And oh, by the way, because our model is in PyTorch is initialized randomly, so we just always set a seed for reproduction. And here's one thing you should pay attention to, which is that the in features, we set our in features at 2 because our dot has a 2D coordinate, and as for the output features, you may want to set it as 16 or 32. Alright, it depends on you. Remember what we said before. Deep learning is an experimental and empirical subject, so just try it. Here we just set it as a 8, and the next layer's input feature should line up with the previous layer's output features. So here we just set it at 8, and our output features should be 1 because we want to predict a label for a single dot, and the label is 0 or 1 corresponding to the green or red. So here our output features is 1. After creating our model, we are going to build a training loop to train our model, enabling it to learn the patterns from the training dataset. And here are some important and necessary concepts you need to know. I know it's boring, but we just have to know it because it's so significant. We use laws to measure how different the model's predictions are from the ground truth, and we use loss function to calculate the loss. Same as a selection of the layers, we also have so many different choices of loss functions. Um, Typically, we need to pick different loss functions according to different specific tasks. Here, our task is actually a binary classification task, so we just need to pick the BCE with largest loss as our loss function. And if you're interested in the exact mathematical process, you can check the documentation. But for now, I think we can just skip the details because, our main goal is to learn the idea of deep learning. And you just need to know that we pick it as our loss function to calculate the loss. Basically, lower loss usually means better fit, so we just need to minimize the loss. How can we do that? The answer is backpropagation and optimizer. The backpropagation computes the gradients of the loss with respect to the model parameters, and and then we use the optimizer to update the parameters based on the gradients. The optimizer is actually different kinds of algorithms. It decides how we, update our parameters. And here we just pick the SGD as our optimizer. Let's look at our training loop function. It has parameters, the model we want to train, the training dataset, the epochs, and the loss function optimizer and target device. And the training loop is just like what we talked before. We make prediction, use our model, and calculate the loss, use our, a loss function between the prediction from the model and the ground truth from the training dataset. And then we use optimizer zero grad to set, this method clear the history of previous gradients, and then we do the back propagation and we use optimizer to update the parameters, and we can also print some information during training so that we can observe the process of learning. Finally, let's train our model, use the training loop, and before retraining we can set the target device using this device agnostic code. If we have GPU, then use GPU, otherwise use CPU. Yeah, that's good, we have a GPU. And use our training loop function, and we set the epochs at 1000, and as we mentioned before, we use the BCE with largest loss as our loss function, and we use the SGD algorithm as the optimizer, and we give it the model parameters, and we set a learning rate as 0.1. By the way, the learning rate is controls how fast our optimizer update the parameters. You can think it's just like the step size. Let's run our code. Oops, what? Name training loop is not defined, sorry. Let's run our training loop. Okay. Wow, look at that. Do you remember what we said about loss? Loss is the value to measure how different our prediction from the ground truth. We want to minimize the loss. And look at that. It's decreasing. What does it mean? It means our prediction is closer and closer to the ground truth, to the target label. Wow, that is the magic of deep learning. Finally, we train our model, and now we can use our model to make some predictions to check whether it's a good model. But before that, there's one thing I want to let you know, which is that actually the prediction of our model is not what we expect. we can just check it. Y logis, and let's just pick the first 5 prediction, and is positive, negative, positive. Oh my god, what is like? What's it? Do you remember what we expect? We expect labels. Y test, and we pick the first 5. Yeah, 1010 corresponding to red and green. But it does not look like what we expect, so we need the sigmoid function to convert the row logits into the probabilities, and then use the round to convert the probabilities into the labels. Let's check it. Probs. Whoa, look at that. Is 0.94, and this one, that means this one has 94% probability of being red, and the second one, it means it only has a 30% probability of being red, so it's more likely to be a green dot. And finally, we use the round to get labels, the round method. Let's check it. Pred labels. Well, look at that, 10101. It's totally same, 10101. Yeah, that's the format that we expect. And here's one thing is very important and interesting. Do you think just looking at the numbers, do you think just looking at the numbers is boring? Me too. So let's visualize it. And there's a plot decision boundary function to help us visualize the prediction results. But, we can just ignore it and focus on the idea of deep learning. I will share this file if you want to know how it works exactly. But for now, we just directly use it. Let's visualize it. Run it. Oh, sorry. Name not defined. Sorry for that. Wow, look at that. It's such a beautiful plot. And there's a decision boundary to separate the red and the green. But do you think it's a good decision boundary? No, obviously not, because there's misclassifications. How to improve it? And we can just train more epochs. Let's train one more 1000 epochs. Do you see that? The loss is keep decreasing, and let's check the decision boundary again. Wow, it's become better. And let's train it one more 1000 epochs. The loss is keep decreasing, and the decision boundary becoming better. So that's the magic of deep learning. This example is quite simple, so the training is fast, but in practice, a model can be, much deeper, and the training can be very time consuming. So we can use torch save to save our trained model so that we don't need to train it again when we want to use it. And then we can use the torch load to load the saved model and use it to make predictions without training it again. Let's run it. This is our model's path, and you can see that we create a models file, and we save our model and check the corresponding directory. There's a my model version v0, and we can load our model, check it. Wow, it's same as what we trained before, and use it to make predictions. Oh, it looks good. And we do not train it again. We just directly load the saved model and directly use it. Whoa, congratulations! You already know the basic idea of deep learning through the PyTorch workflow. And here's a bonus section. Do you remember we instantiate our model and we train our model for 1000 epochs, and we use our model to make predictions and we visualize it. This is the results after training for 1000 epochs of our model. And as we mentioned before, if we want to improve it, we just need to keep training for more epochs. But besides that, are there any other ways to improve it? Yes, of course. We can adjust the structure of our model. And let's go back to define the model classes, and we can add an extra layer. Let's call it hidden layer. And we still use a linear function. The linear layer. The input features should line up with the output features of previous layers, so it should be 8, and the output features should line up with the input features of the next layer, so it should be 8. And we also need to adjust our forward function. And after the input layer, apply the ReLU function, and we can pass the data into the hidden layer, and we can apply the ReLU function, self ReLU, and finally we pass the data into the output layer and we get the results. That's all the improved model, and let's define it, and we instantiate it, input layer, hidden layer, output layer, our activation function, ReLU. Wow, it looks good. And now let's train the model again for 1000 epochs. Look at that, velocity decreasing, and we test our model and visualize it. Oh my god, did you see that? Both of these models are trained for 1000 epochs, but our second version is better. So with this example, you can know that how you design your model is really important. Okay, alright, that's all. Thank you for watching, and if you like this video, please leave a like. This is my first video and there are still lots of things I need to improve. If you have any questions or found any mistakes in this video, please leave a comment. And we can learn together and discuss. See you next time.